Our Hot 3D session. Hot 3D is where we give hardware vendors the opportunity to talk about their innovations in architectural design. And this year we have one excellent presentation by Simon Fenney. Simon is with Imagination and has been there since 1992 in the Power VR division. And he will be telling us about how the architectures for hardware ray tracing at Imagination have evolved over time. So, Simon, whenever you are ready.
When the plug wants to go in.
Everybody give one round of applause for Simon.
Hi, thank you for the introduction. As I said, I'm Simon. I'm a research fellow at Imagination, and I've been with the Power VR division since its inception nearly 31 years ago. So in this talk, I just want to cover the hardware ray tracing that we've been doing at Imagination for over a decade, from some of the early systems such as Parsec and Wizard, through to Photon, the latest technology we're offering to our customers. So what I'll like to look at some of the principles that remain relatively constant throughout, as well as some of the differences. Oh, and very briefly, if you're not familiar with Imagination, we develop IP, e.g. graphics, AI, and CPUs, and then license them onto third parties to include in phones, computers, cars, TVs, that sort of thing. So a little bit about Imagination, Caustic graphics. Now, as this talk is, part of this talk is retrospective, well, at HBG 22, Aaron LaFond suggested using the DeLorean to go back in time, but as this is for ray tracing, I figure an axis-aligned police box seems more appropriate. So Power VR began in 1992 as a project within Imagination, previously called VideoLogic, previously called Teletype. It's been going for ages, really. And the aim was to develop efficient rasterized graphics hardware, basically tile-based deferred rendering. Now, Caustic Graphics began in 2006, and their aim was to develop efficient ray tracing, and we saw that their philosophies and aims were very much aligned with ours, so they became part of Imagination in 2010. Now, this bit's a bit of a show and tell. In 2009, they released, Caustic released Lux, which was an accelerator board for 3D visualization of ray tracing for the professional market. And that handled about 25 million incoherent rays per second. And I'll get onto incoherent if you're not familiar with that. And that was basically the FPGA predecessor of Parsec, basically one of these things, which was a parallel BVH and triangle accelerator using a 90 nanometer ASIC, so not super sophisticated at the time, and it did the shading on the CPU. So there were two products, Caustic 2100 and 2500. So this basically handled around about 100 million rays per second on a 65-watt board. Then in 2015, along came Wizard, which is basically a full mobile-sized GPU. So a battery class, I think, was what Peter Shirley referred to them. And that was doing over 100 million rays per second. The peak was much higher, actually, on a 2-watt, I think, SoC. So basically something you would have in the phone. The GPU was effectively a phone GPU, but didn't make it into a phone product, unfortunately. And then in 2021, we announced Photon, which is basically even smaller and or faster than the previous, which is kind of looking at 160 to 480 million rays per second, depending on the config the customer wants. So a brief diversion onto incoherent rays. So primary rays that you fire out through the camera, basically rays coming from neighboring pixels, pretty much will do the similar things as they go down through the BVH. They'll visit the same nodes for a lot of the way. Then you get onto secondary rays, and they rapidly become less and less coherent with bounces. They're going all over the place. And then if you do stochastic global illumination rays, well, you've got no chance of them being coherent. And your cache and memory subsystem will basically be tortured if you don't do anything clever. So just want to look at what has remained in common between sort of the various generations, and we'll concentrate on three things. There's the automated hardware BVH traversal and triangle testing. There's ray and geometry coherency gathering so that you don't murder your memory system. And there's also shader coherency, basically so you're friendly to your SIMD. Now the BVH traversal, so all the generations basically traverse their acceleration structure automatically. So the rays were tested against bounding volumes and triangles, or you could also launch procedural operations if you got to a enclosed bounding volume that's marked that way. But there have been changes. So Lux and Parsec both used bounding volumes which were made from the intersections of 2 or 3 spheres, which is great for snooker scenes. You could mark a sphere as terminating, but it's pretty awful for BVH building. So Wizard and Photon very wisely moved to AABBs. Now those are in our hardware are compressed format, so basically each node contains 4 or potentially more sub-boxes, and for that you don't need full float precision. Now we also have what we call coherency gathering, which avoids thrashing the memory system. So if you consider your acceleration structure, your BVH, you need to be able to deal with completely arbitrary rays going down through it. So the systems basically maintain n packets of work, and where each packet has an acceleration structure node ID, where you are, plus a list of the rays that you want to test against the contents of that node, for example, AABBs. So the system picks out a packet using a heuristic. For example, if it picked out node B, then it will want to test rays, say 5, 99, 787 against it, against children E, F, and G. And so any hits that correspond to a box, so for example, if 787 intersects box E, that would then get added to E's packet. Now the packets are all completely dynamically managed, so as they become empty, they will get released into the system and be able to be added to other things. Also, triangle nodes can update the extents of the ray so that later tests can eliminate boxes if they're further away. Also, we do shader coherency, basically to be friendly to your SIMD. So this has been part of Imagination GPUs for Yonks. So PowerVR Series 2, even say Dreamcast era, we would reorder the shading work so that it was coherent. So if we saw that there were n scattered pixels in a tile, all using a particular texture, they would be grouped together and operated on coherently. And then the same thing happened then with shaders. And that's all automatic. You don't have to worry about trying to do the sorting yourself. And it's the same with ray tracing. You don't want low occupancy of your shader units, so Parsec, Wizard, and Photon all do sorting and gathering by the shader. So to make hardware useful, you need an API. So around 2010, we introduced OpenRL, which ran on Lux, Parsec, and Wizard, and that was derived from OpenGL ES2, so it was aimed to be familiar with developers. And that was a full ray tracing model. You had frame shaders, basically ray gen, vertex shaders for doing your object placement, and then ray shaders for basically shading your hits, closest hit shader, for example. You could also do hybrid rendering, but it was a little bit inelegant. So later there was an OpenGL ES extension which basically supported both. Now, a brief diversion. So everyone knows ray tracing is recursive, isn't it? Well, if you, like me, were writing a ray tracer professionally in the late 80s on an array of transputers in Occam, which is a parallel but non-recursive language, or like Andrew Garrard, my colleague who was developing ray tracing hardware and you didn't want to stack shaders, or Caustic in the noughties, also wanting lots of rays in flight, then you might use fire and forget. So the basic concept is that each ray has an address, e.g. a pixel location, where it wants to write its results. It has some RGB attenuation weights and possibly also recursion depth. And then when a ray hits a surface, you immediately fire all new reflection, refraction, shadow rays, attenuating the ray weights appropriately. Perhaps you also do any local ambient lighting and that sort of thing, and then in that case you accumulate back to the pixel. And then you exit the shader, never to be seen again. Well, never to be seen again in this sense. And then the other rays that you've launched will come along and do their work at a later stage and accumulate their results back into that pixel. So back to API evolution. Well, the OpenRL and OpenGL extensions weren't getting any traction. Basically, imagination simply aren't loud enough. But when Microsoft and then Kronos step in, there was suddenly a lot more interest in ray tracing. And perhaps the biggest change here is that it's a very CPU-like recursive model. You stack your shaders. Basically, fire and forget was fired and forgotten. So Photon is designed to support these newer APIs, both Ray Pipeline and Ray Query, and it does the instancing with top-level acceleration structure and BLAS. We actually had considered instancing previously, but assumed that everyone would want to do skinning and stuff, which would be a complete nightmare. So we hadn't considered doing that before. Okay, so what has evolved? What have we learned along the way, and how did we make Photon even smaller? Well, so as I said, Wizard and Photon both use AABBs, but Wizard uses Pluka coordinates. There's an interesting talk by James McComb at SIGGRAPH 2013, which is well worth watching. So in Pluka coordinates, you basically test the ray against the box's 6 silhouette edges, all in parallel, which is great for hardware. And that the system trades divisions for multiplies, because multiplies are cheaper than divisions. And in Wizard, you basically that required 15 multiplies, 9 adds or subtracts. And they were made to be conservative, so you rounded down and rounded up appropriately. And they also included the ray interval test. Now, we wanted Photon to be smaller, so we wondered, can we do the ray ABB test with less hardware? So going back in time again, we revisited other ray ABB tests, Kajia's and Smith's, and that reminded us, well, it reminded me, because most of the team are younger than PowerVR, of how the Series 1 rendered objects. So they were basically built out of the intersections of planar half spaces, and the graphics library gave the hardware all the front-facing faces and then all the rear ones, and then for each pixel, it found the furthest front face and then the nearest rear plane and made sure that the front was in front of the rear. So we wondered, could we use this to do less work, i.e. use less silicon, though possibly with higher latency? So in the Photon ray box test, we translate the AABB by the ray origin, so everything's kind of moved into local space. Then we make the ray direction, sorry, this is a bit of a deep dive, I apologize. Then we make the ray direction canonical, so basically permute the ray and ABB axes and flip the signs so that the ray direction is always positive and that Z is greater than Y and that Z is greater than X. Then in effect, we kind of scale by 1 on Z and compute the inverses. So in effect, the ray direction becomes Z divided by X and Z divided by Y, 1, which needs 2 reciprocal operations and 2 moles. That cost is amortized over multiple AABBs. But what of division by 0, you scream? Well, we'll get back to that. And FP precision and consistency, well, we used exactly the same operation for the ray triangle tester, so everything is consistent. So, and I apologize, much of this was done during lockdown, so it's a little bit hazy in my memory. But to be safe, the AABB is expanded, basically by setting some bits in the floating point, to include the floating point error of the AABB testing, and also the worst case error that you get with the ray triangle tester, because you don't want holes in your geometry appearing. The first thing it does is it checks the Tmin and Tmax of the ray against the octants, so you can do an early out. I say early out, but you can't actually skip stuff in a pipelined hardware. So what it really does is just clock gate the remaining hardware so that it doesn't do any calculations and saves power. Then it computes the distances to the box planes. That just needs 4 moles because Z is effectively free because we've scaled it that way. And then we get the max front distance and the min of the rear, and just basically make sure rejected if the front is greater than the rear. And we again bake in some conservative safety margin. And also do the T-min, T-max test. So how do we deal with those meddling zeros? Well, the AABB test has to be conservative, so we can make it a little bit more conservative. Now, as we're specifying the hardware, we can basically start with IEEE float and then add more exponent bits. So we introduce these special infinitesimal values which are less than the normal float min. And then any zeros in the stuff are remapped to those values. And then all the messy cases are completely mopped up by just doing normal floating point exponent calculations. Now, to compensate, you don't need all 23 bits of the mantissa in the AAB test. It really is overkill. So we can basically prune off some of the bits there to get some area. So some other changes that happened with Photon relative to Wizard 1, we added the instance transform unit. So if you want to do instancing, the bottom level acceleration structures, they're placed in with standard sort of matrices. And so you don't transform your geometry because that's expensive. You instead inverse transform your ray. So you could do it with that sort of matrix. But we don't do that. We do it in 2 stages. We basically do an inverse translation first, followed by the inverse rotation and scaling. Now, that loses you some fuse, multiply, add convenience, but it gains accuracy where you need it. And some things were removed. So Wizard had a hardware BVH builder called the SHG, and that built the acceleration structure on the fly. As the vertex shader output batches of triangles, it would gather them up and sort of merge as needed into a hierarchy. But any silicon and an SoC is money, so Photon instead uses compute. Other things we did. So both Wizard and Photon test rays against triangle pairs. I've been harping on about this all week. So we have a dual triangle tester. But using the tricks we learnt from doing the AAB tester, we've managed to reduce the number of maths ops relative to Wizard by quite a bit. But that's probably a whole talk in itself. Anyway, so what's the sort of overall architecture? So in the system, we can have some number of what we call racks, the ray acceleration cluster. And sitting in the center of that, you have a box primitive scheduler. So what that does is it grabs a packet out of the packet system and gets the rays which are associated with that and sends them on to either the dual triangle tester, the ABB, or the procedural tester, gets back results, updates the packet, etc., getting data out of a cache for the acceleration structure. Any rays that then actually finally hit their final triangles are then put into a ray task scheduler to make sure that we try and keep similar shading operations, as many similar shading operations being sent to the shader units as possible to keep it fully occupied. But this is graphics, so we need some pictures. So this is basically one of these. This is a dead one, unfortunately. Wizard 1 sitting in a small Linux machine. It's, again, a mobile class GPU, so very low powered. And this is a demo that was basically videoed off the screen. The captures unit decided not to work, so it's from an SLR, so I'm sorry about that. So it's your typical, let's do lots and lots of reflections off curved surfaces, shadows. There may be a couple of bounces. There's no collision detections, as you can see. And the surface is also bump mapped so that the reflection rays are kind of incoherent. Obviously, we've got like a glossy, not smooth reflection on one of the teapots. And a second one, if that wasn't obvious enough, that it was ray tracing, you can write it in massive great glass letters. And obviously this one's also got proper translucency, refraction, that sort of thing. So I think this must have several bounces. Unfortunately, I don't know who wrote the this demo, so that there's obviously quite a few levels of height of recursion in this one. I say recursion, but this was using fire and forget, so there really wasn't any recursion. Okay. Now, I can't show you Photon running because it's not physically made yet. I think David McAllister said it would be a little while before the work he's working on now would become. In the SOC IP licensing, it's even longer. Now, this is a hybrid ray tracing demo because we kind of expected on the mobile end, a lot of the demos that are ray tracing will actually be hybrid. So this one is just showing that you can do GI effects using ray tracing and light probes. So basic idea, you got a scene, the wall on the left is basically contributing some lighting to the wall on the right, and as the, I think it's either a cloud or a giant balloon going overhead, shadows it, it changes the lighting on the right. I mean, people should be all quite familiar with this. And to emphasize the fact, just take away most of the texture. But basically, you can see as the shadow moves away, it starts becoming more and more yellow, as you'd expect. And then, come on, it's going to do it in a moment. It's just sped up. As you change the material, obviously you get the same sort of effect over on the wall as it changes. Okay, another again hybrid demo. This time it's ray tracing from the GBuff, and the idea was to show, it's not really very visible, but you can either use the traditional shadow maps, but you've got to obviously pick the right version of the umpteen different shadow map algorithms so that you get you try and avoid any jaggy artifacts from undersampling. But why not just fire rays? It's just easier. Alternatively, and then, sorry, in this one also showing reflections. Now this is unfortunately a bit too subtle, but basically the floor, the piece of art, and the entirety of the diver are all reflective. Kind of, there's like another example up there that's sort of showing what's going on. So he's reflecting the entire, or the whole thing's reflecting the entire scene, which obviously is a bit more painful if you try to do an rasterization by updating cube maps, et cetera, et cetera. It's just all done in one fell swoop. And that's the end of the demos. And just like to say some acknowledgements to the various colleagues, past and present, who helped fill in the gaps in my knowledge. And thank you. There's any questions?
Thank you, Simon. We have a little bit of time for questions. There's one. I think I can't throw that far.
Awesome talk, Simon. Really enjoyed it. Could you comment a little bit on the cache hierarchy of the different hardware through the generations? Because this is really important usually.
To be honest, I only know what the cache height... Well, okay. I don't know what was happening in Parsec. No idea. In Wizard, it will be very similar to Photon. So there's a acceleration structure cache just for the ray tracing, which then pulls in data from a more of a system-y level L2 sort of cache. I know we tend to get about a 90% hit, well, I believe we get about a 90% hit rate on that cache. So it's quite an effective thing for reducing your external bandwidth, which on a mobile device you want because it uses a lot of power. I think that's basically, it's just nothing more sophisticated than that, really.
Okay, thanks a lot.
Behind you.
Thank you for the great talk. Do you have a comment on how the hit rate changed from moving from spheres to ABBs?
No, that's way before my time. Probably quite significantly, because I know what I feel that the peak rate of that particular chip was a lot higher than the measured values that they were getting. So I suspect that it's not great. It is painful trying to build an acceleration structure out of spheres.
Fair. Thank you.
For questions? Yes. Can you photo?
Where?
Take a pic.
Whoever grabs it.
Okay, my question is about passes. So a lot of ray tracing APIs are based on rays. You give it a bunch of rays and it gives you intersections. But is there any kind of benefit of having passes where all the next ray basically starts where previous ray ends? And is there any benefit of knowing that and somehow utilizing that knowledge?
Well, there's nothing stopping you once you've got an intersection firing another ray immediately. I mean, the hardware we've got wants you to throw as many rays as you can at it as possible. We've certainly seen some benchmarks which aren't firing that many rays, which is quite disappointing. It's hard to keep, it's hungry, it wants to eat rays. So you need to keep it fed. As long as you're, I'm not really sure. I mean, as long as you're giving it rays, it should be fine. I mean, it's going to try and find the coherency of things and test them and try and keep the system running efficiently.
Maybe I didn't phrase my question properly. Basically, the question is, when you do intersection, you already know where in the BVH you are. So where is this intersection in your BVH? And for the next ray, you basically kind of throw away that knowledge and you try to start it from the scratch to first find where you are in the BVH and then continue from there.
We do that. We don't currently try to take advantage of where you're starting from. But it doesn't seem to matter too much. I mean, if you're assuming that your rays are going off in another direction, it's probably only going to be, maybe you lose a little bit of efficiency on a few top levels of your acceleration structure. But it doesn't really, after you've got past that, you're kind of back to where you would get if you kind of had some extra information to say, I'm starting here, use a different acceleration structure. Okay. If that's what you're asking.
Yeah, thanks.
Okay, last question.
Yes, but basically it's impossible or very difficult for BVH, so I agree. But my question is about power efficiency, because if I remember from slides, it was 2 watts power consumption, which seems to me amazing, so very great. So can you somehow compare, for example, for one ray, the power consumption with some competitive solutions, or?
I know there was a demo that had a competitor's hardware of the same vintage as this doing the same test. Now, I'm not sure whether there may have been a couple of these boards in the machine. So unfortunately, I can't find the people people move on. But if it may have been 4 of these boards in there. So that would be what, 8 watts possibly of GPU. I can't count the memory. And it was running much faster than something which was a 200 or 400 watt board. Yeah. So is that good enough? It's basically, let's see if I've got it. It was basically this was basically written and were running on both the Wizard card and a bigger GPU than we make. And yeah, it was running faster.
Great, thank you.
Okay, in the interest of time, let's move on. Simon will be around, so you can ask him all of your questions still. I would like to call out that this session has been organized by Erin Noll, who is not here today, so I am session chair. But let's give another round of applause for Simon and for Erin.